So in 9.4, we're going to learn about direct and inverse variation. So this is a concept that is on a lot of standardized tests, like the SAT. It will be on the SAT. So it's pretty easy equations, not hard to memorize at all. So direct variation, it says a relationship between two variables, x and y, that can be written in the form y equals k times x. Okay, where k is not 0 and is called the constant of proportionality or constant of variation. Okay, so k is what we call a constant. It's going to be the same number throughout the problem. So once you find k one time, you're going to continue to use that k throughout that problem. Okay, so the way that you would describe like direct variation is when one value goes up, guys, when one value goes up, the other value goes up. Okay, so an example, like this is kind of silly, but an example is this like little chart at the doctor's office. Do you guys know the little chart at the doctor's office? Don't you guys hate that? The doctor's always like, rate your pain. And I'm like, I don't know. I came in here because I'm coughing. Like, I have no pain. 0. So it's based on if your pain is up, then your score is up, right? So that's a direct variation. So I always tell a cheesy story. So I have a cheesy story about this. So when I was in grad school, my grad school friends, we would always get together and we would like play cards and like board games because I'm the queen of games. So we were playing cards, and a friend of mine, Megan, who's an amazing baker, in her fridge had an entire bowl of cookie dough, and she hadn't baked it yet, but she was going to bake it the next day. And our buddy saw the cookie dough and was like, "Oh, can I eat this?" And she's like, "I guess. Like, go ahead if you want to." And so he started eating it, and he was like, "Oh my gosh, this is so good. I'm going to eat this whole bowl." And she was like, "I probably wouldn't eat the whole bowl. You're going to get sick." And he was like, "Challenge accepted. I'm going to eat this whole bowl." So he did. He ate the entire bowl of cookie dough. And in grad school, we all have like classes that we teach. Like that's part of, like we got grad school for free because we taught at IU and got free tuition basically, so for teaching classes for them. And so he taught an 8 a.m. class, which was like the worst for grad students. We hated teaching 8 a.m. classes, just like you guys will hate going to 8 a.m. classes someday. And so he ate all that cookie dough and was like, "Oh, I gotta go home. I'm gonna teach at 8 a.m." And then I get a call at 7:30 that says, where he's like, "Oh my God, I can't teach right now. You're the only person that's answered the phone. Can you go teach my class?" And I was like, "Great. I'm really glad that I answered this phone call." So I go and teach his class, and his class was kind of like, "Where's our teacher?" And I told him the story. I was like, "Well, he's really not very smart." So in that day, we were learning about direct and inverse variation. So his class really started teasing him, and they were like, "The more cookie dough you eat, the more you feel sick, right? The less in your stomach, right? The more cookie dough you eat, the less in your stomach. That would be inverse variation. Does this make sense? So the more something goes up, the more the other one goes up, that's direct variation. The more something goes up, the more the other thing goes down, that's inverse variation. So can you guys think of examples? You don't have to do cookie dough examples, but what are some examples in real life of direct and inverse variation? The more you what? Yeah, the more your temperature goes up, the more sick you are. The higher your metabolism, maybe the more weight you lose or the lower weight you are. Maybe, I don't know.
The more I exercise, the more tired I get.
The more Kyle exercises, the more tired he gets, right? The more calories you would lose, yeah. The more clothes, the more laundry you have, or the more clothes that you wear throughout the week, the less you have in your closet. It's an inverse. Yes, the faster you run, the less time it takes for you to get to the finish line. That's an inverse variation. So rate and time, right? So do you guys understand these? So direct and inverse? Okay, so we're good. So number 1 says, write an equation that expresses the statement, the cost C of a dozen donuts varies directly as the price P. So cost C varies directly as the price P of one donut. So C is equal to K times P. Do you guys know what the constant is in this case? So the total cost of a dozen donuts is equal to the price of one times some constant. Well, what would the constant be? It's 12. It's a dozen, right? So it's C equals 12 times P. Usually, though, at donut places, you get a deal if you buy a dozen donuts. All right, so it says M varies directly as Z. So when it says M varies directly as Z, we automatically write down M equals K times Z. So some constant times Z. So the bigger z gets, the bigger m gets. So if m is equal to 120, when z is equal to 15, are we able to solve for k? Yeah, we can divide it out. So you can do 120 divided by 15. Do you guys know what that is? No, it's 8. So now that is our constant. So this is our constant. So what a constant means is it's going to be the same throughout the rest of the problem. So we rewrite, this is m equals 8 times z. This is now our direct variation equation. So I'll say that sometimes, like on the test, I'll say, write the new direct variation equation. Once you find the constant, write the new equation. So we have that, and then it says, write an equation and you use it to find the constant of proportionality. So we did that. Now if I said, find z when m is equal to like 360, right, you would then be able to do that. You would just plug in 360 to find the z. Okay, and that's how the next ones are. EG? What did I do? Oh, equation, sorry, EQ. All right, so the terminal velocity of a parachutist is directly proportional to the square root of his weight. This is kind of like a real life example, but it's kind of a morbid example, right? So the faster a parachutist goes is directly related to his weight, right? Oh my God. I know, but luckily it's not that big of a difference. All right, so a 170-pound parachutist attains a terminal velocity of 9.2 miles per hour. So let's write the direct variation equation. So the terminal velocity, we'll call that v, of a parachutist is directly proportional to the square root of his weight. So we're going to have the square root of w in there. So we have v equals k times the square root of w. So we need that constant of variation in there. So directly proportional to the square root of the weight. So 170-pound parachutist, 170 pound, attains a terminal velocity of 9.2 miles per hour. So we're going to find k. So we're going to do 9.2 divided by the square root of 170. So you guys can do this on your calculator. Nope. All right, so we have that. So we have k is equal to 0.7056. And I have other decimals here, so I'm going to do dot, dot, dot. And I'm going to keep that number in my calculator, okay, because I want it to be as precise as possible. You can store values on your calculator, too, if you want to. I think we've talked about that before. So it says, what is the terminal velocity of a parachutist weighing 250 pounds? So we want to find the velocity when we have 0.7056 dot, dot, dot as our number. So now we're going to plug in that 250 pounds. So I'm going to take that answer that I have in my calculator and I'm going to multiply by square root of 250. So answer times square root of 250.
Why'd you put this dots?
Because I just wanted to indicate that I had that stored in my calculator. You don't have to do that, but
Are you multiplying?
yeah, we're multiplying. Yeah. So I have that stored in my calculator, and then I multiplied by square root of 250, so I get 11.157. And I said round to the nearest tenth, so 11.2 miles per hour is how fast they'd be going. Yeah, it's really not that big of a difference, right? Luckily. That would be scary if it was a big difference. We don't want someone going like 30 miles per hour when they hit the ground. That would not be good. All right, so luckily it's the square root of the weight, right? All right, so that one you can actually set up with a proportion. So do you guys remember proportions from geometry? Like you could. So direct variation you can set up with a proportion. Inverse variation, it's a little bit harder because basically it'd be a proportion where you like flip the other one. So really it's kind of best to know these equations, to know the k times, so y equals k times x. And then the inverse one will be y equals k over x. All right, so it says if y varies directly as x, and y is equal to 27 when x is equal to 6, so y varies directly as x is y equals k times x. Y is equal to 27 when x is equal to 6. We divide the 6 over. We can reduce out by 3, so 9 over 2. So we get y equals, so our direct variation equation is y equals 9 over 2 times x. Okay, so what does this look like? If I was going to sketch this as a graph, what is it? Yeah, Eric? Yeah, y-intercept is 0. Up 9 over 2. Exactly, it's a line with a slope of 9 over 2, right? Going through 0, 0. So up 1, 2, 3, 4, 5, 6, 7, 8, 9 over 1, 2. And you could also go down 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 over 2. I'm off the graph. And then you can sketch it in. Oh, I really need a ruler when it's like this. This is not going to be good. I tried. All right, that's our direct variation. So a direct variation, it creates a line. Does it make sense that it would make a line? As one value goes up, the other value goes up, right? As one value goes down, the other value goes down. Perfect. Yeah, it makes a line. All right, so inverse variation. So there's a reason why this is in this chapter. So inverse variation, it says the relationship between two variables x and y that can be written in the form y equals k divided by x. So think about it. If you're dividing by a really big number, like if x was 100, if I divide out by 100, it makes my other number really small, right? So that's what's happening. The bigger x is, the smaller y is. Okay, that's why it's an inverse relation. So it says write an equation that expresses the statement Sam's speed r is inversely proportional, so equals k over to the time t. So r equals k over t to the time it takes for him to cross the finish line. And this makes sense. So my cross-country runners, every single time, they run 3.1 miles, right? And the faster someone goes, doesn't it take them less time to get across the finish line? Exactly, right? So they're an inverse relationship. And that k ends up being the distance that they're traveling. So they're traveling 3.1 miles every single time. All right, so number 2. So it says y varies inversely as x, and y is equal to 4 when k is equal to 5. So when we see y varies inversely as x, we immediately write y equals k over x. And y is equal to 4 when x is equal to 5. So what's k? Multiply the 5 over, so we get 20, right? So our inverse variation function is y equals 20 over x. So when it says inverse variation function, that's what that is. Okay, so this is a little bit harder. So when I student taught one time, I had the sweetest student teacher, supervisor. I had 2 of them, actually. One of them was actually kind of mean, but I had a really nice one, too. And she was teaching her students that this was a line as well. It was just a line that went downwards, right? Which kind of makes sense, because as one value gets bigger, as x gets bigger, y would go smaller, but it's not a line. Do you guys know what y equals 20 over x looks like? No? Let's see. Let's graph it. It is kind of a conic section. All right, so let's see. So let's say I plug in numbers like 1, 4, 5, 10, right? All these numbers are nice. Maybe 2. Plug in 2. Maybe I'll squeeze that in there. So 1, 2, 4, 5, 10. These are all numbers that are divisible by 20, so they're good numbers. So when I do 20 divided by 1, I get 20, so that's way up here. 1 comma 20, way up there. 2 comma 10.
Oh, is it exponential?
4 comma, what do I get when I plug in 4? 5. So 4 comma 5. 5 comma 4. 10 comma 2. And then it kind of curves, right? All right, and if we plug in negative numbers, what if I plug in negative numbers? So negative 2 comma negative 10. Negative 4 comma negative 5. It basically ends up being the same thing, just over in the third quadrant. So negative 2 comma negative 10. Negative 4 comma 1, 2, 3, 4, 5. Negative 5 comma negative 4, and so on. So it's going to be like that. It's a reflection of that. Okay, so this is a hyperbola. So it is a conic section. You were right. Good guess. So it's a hyperbola. Okay, it's just not quite the hyperbolas we did in class. Ours were always like perfectly up and down or perfectly right and left. It involves a rotation. So we didn't talk about those. Okay, so, and the last thing we have to talk about are combinations of these. So if I have like joint variation or combinations of variations, it will basically say what it's going to do. So it says a relationship among three variables that is read. Y varies jointly as x and y. So if it's varying jointly as something, that means as both of those things go up, then the other thing goes up. So the way we write it is y equals k times x and, I think I said x and y, but x and z, right? So y varies jointly as x and z. So don't forget your constant of proportion, though, your k. So it's all together. And a lot of things vary jointly. A lot of times it deals with like the cost of items. So it says the cost Z of printing a magazine is jointly proportional to the number of pages P in the magazine and the number of magazines printed. Okay, does this make sense? Let's think about it. The cost of printing a magazine, wouldn't it matter how many pages there are in the magazine, but also how many magazines you're printing? Totally, right? So the cost C is jointly related to the number of pages and the number of magazines. So find the constant proportionality if the printing cost is $62,000 for 4,000 copies of a 150-page magazine. So we set it up like that. Oops, 4,000, not 400. So we take our 62,000 and we divide by, I think it's like 600,000, right, when we multiply that? So we get K equals 0.10333 and so on. Okay, let's think about what that is. Any ideas on what that is? Karen? Yeah, Kyle got it. Yeah, the cost per page. It's 10 cents to print each page. Okay. So how much would the printing cost be for 5,000 copies? So we're going to plug that number back in. And now we're saying that we have 5,000 copies of a 90-page magazine. It's going to be like that. So I take that number in my calculator because I rounded. I'm going to multiply by 90, multiply by 5,000. And I get my total cost is $46,500. Okay. And then the very last thing we have are combinations of these. So maybe something varies inversely as one thing, but directly as another. Okay, so it says a relationship between three variables x, y, and z that contains both inverse and direct. So there's lots of different examples of this, but if I say y varies directly as x, I would have kz, or sorry, it's kx, but then also inversely as z. I don't write a second equation. I've put this on the test before and people try to write two equations. It all goes together. So and inversely as z, where do you think we put z? Just down here, right? And inversely as z. So it's all together. So directly as x, but inversely as z. So x is on top with the k, and z is on the bottom. And this will happen a lot in science. So it says the resistance R of a wire varies directly as its length, so K times L, and inversely as the square of its diameter. So what do I put on the denominator? Just D? D squared, the square of its diameter. Okay, so that would be an equation that would represent that. Does this make sense? All right.